Hi everyone, we are from University of Magdeburg, Germany, and we would like to present a solution for information propagation in schema matching and entity resolution for heterogeneous data.
So for the motivation of our work, we thought of taking a really big picture. And we thought that it would be nice to remind the audience that our ability to find connections between data items is truly essential for everyday human progress.
And in the data domain, data integration is a practice that supports our ability to find insightful connections. It offers users with consolidated interface, which appears to be working with single data source, but in reality, it is working with heterogeneous data sources. Given that these tools are really important, there are groups like DI2KG that seek to help build the next generation of production-ready data integration tools. So we summarize our experience with the submission for ER and schema matching challenges of DI2KG 2020.
In essence, we are prepared for solutions, 2 domain knowledge-based and 2 early machine learning-based solutions for the schema matching and entity resolution challenge, and we talk today about them.
So moving on to challenges and dataset. Here is the task to establish group of items that refers to the same real-world entities.
Whereas schema matching is the task of identifying mapping of attributes from source dataset to the attributes of target dataset.
Our dataset has a product specification from 26 websites consisting of approximately 16,000 JSONs. Ground truth of entity resolution covers approximately 4,000 JSON pairs, where smallest file was only 161 bytes.
The dataset is also highly heterogeneous, which has redundant fields, and it also contains non-product and unidentifiable items. There are variations in names and units, and it also has multilingual and wrongly parsed data. As you can see here that one of the files contains correctly mapped pair of attribute names and values, whereas the other one contains all values mapped to a single attributes.
Each site has from 6 to 883 unique attributes, with total of 3,715 unique attributes. Ground truth for schema matching contains only 135 items with no information about 24 target.
Moving on to our domain knowledge solutions. These are algorithms that we developed. For entity solution, we started with the key insight that brands and models actually identify monitors uniquely. First, we started with explicit brand naming. So we looked at all fields that we thought could have brands, and then we looked at the values inside. We did this, we were able already to cover 8,000 items. After that, we took the brands that were identified and we tried to find them in the titles. We found 321 items, with 149 items being finally considered unbranded or generic. For model identification, our assumption would be that we would have much more models than brands. We developed a 4-step algorithm with a strategy that we wanted to propagate information which is more certain before information that are less certain. Right? So to do so, we developed, as I said, a 4-step algorithms that we started with a regular space extraction. So we looked at fields that were likely to have models, such as those, and then we extracted from these fields model names. And next, we sorted the models by popularity, and then we went through the unbranded and less certain data, and we checked whether in the title the popular models would appear for the brand. And we did regex space extraction to find additional models from the page titles. And we again let based on voting, we let the less certain items change in case there was a popularity shift. Finally, we matched popular models on all fields. We could identify 600 items further by this approach. After this, matching was actually done in a trivial way. So we just looked at all models from a brand, and we just pairwise assume all these to be a match. And this led to a competitive F1 score of 0.92. Okay, moving on. For schema matching, we developed a solution that would do instance-based matching and that would do a bit of syntactic matching. The solution consisted of 2 parts. In the first part, we went through all the values of the source attributes and we tokenized. To this end, we used an English parser, even though we also had Italian text, and we also had to remove redundant text and publicity text and redundant fields. After doing this, we did pairwise comparisons. We set a threshold of 75% to determine that 2 source attributes will be a match. We also did syntactic similarity when the items were not deemed to be matched based on their instance-based values. After this step, we basically have a list of paired sources attributes, and we would want to have them into groups such that we can say uniquely this group, all the source attributes in this group match to this target attribute. To this end, what we did was that we did a grouping approach which was based on rules, and that try to form fully connected graphs, such that all the source attributes inside are all deemed to be pairing with each other. Right? And after this, we did syntactic similarity on each group. So the highest syntactic similarity available for each group to the target attributes. From this approach, we still have room for improvements, and some shortcomings include that we did not consider alternative units, so mapping between alternative units for the instance-based values. Taken together, our domain knowledge solutions, though different, have some points in common, which is the fact that they both use some concept of information propagation. That is, they both, to make some choices, they both look around to the choices made by other, in the case of other instances, before they make a decision, right? For example, in the case of grouping here, when the source attributes have to be grouped, matched source attributes have to be grouped, or in the case of model identification, where we do a popularity-based voting.
Our assumption was that title contained all the information required for entity resolution. We took the title of the ground truth and passed it to the pre-trained bird to get the contextual embeddings. We subtracted embeddings of page title and got the representation of relationship between them. And we also removed the publicity text. We used k nearest neighbors, and overall F1 scores on ground truth was 81%. We also used other classifiers, but k-NN gave the highest F1 scores. Further, we could fine-tune BERT as attention mechanism could guide the match on the precise fields that serve identification, such as branch and model. To you.
So let's move on to the semi-supervised schema matching. The motivation behind semi-supervised learning is that the model learns from both labeled as well as unlabeled data. This is not to be confused with active learning. For this model are tokens extracted using topic extraction and TF-IDF weighing of these tokens. Since this approach employs both supervised as well as unsupervised approach, it can be better explained in two phases. The phase 1, the supervised part, we form the clusters using the labeled data and calculate the centroid for each cluster. In phase 2, which is unsupervised part, we use the unlabeled instances, calculate the similarity of that instance with all the clusters which were formed in the supervised part. Now cluster this instance to the highest similarity cluster and retain the model. This process is repeated until all the unlabeled instances are exhausted. In order to solve the multi-label problem, we use soft clustering, which stores the membership of each instance with all the clusters. A threshold of 75% was used to assign the multiple labels to the instances. This approach gave us a F1 score of in the range of 25.4 to 41.5%, but the results of this model are inconclusive. This is due to the lack of the tuning of the model. Thank you.
Okay, so we come to the takeaways and future work. And overall, we developed 4 solutions to the DI2KG challenge, 2 based on domain knowledge and 2 based on machine learning. The earlier results for machine learning solutions are inconclusive in the sense that we have to do more feature engineering, hyperparameter tuning, and even model tuning to be able to be sure of their performance. Nonetheless, we had some insights because we tried a case where we cleaned the data to make the integration task easier for the machine learning tool, but we did it in such a way and to such an extent that machine learning results are trivial to do a matching. And this brings us to something we can call the trade-off between integration and data cleaning, which is that yes, by cleaning your data more, you can make the integration task easier, but you have to do it in such a way that all your efforts are generalizable across data sets. Okay? So this is something important that should be taken into consideration.
Moving on from machine learning solutions to domain knowledge solutions, we found out that we still need to dig deeper into the rules and algorithms that we used and find out how they contribute each other to the overall goal of our integration tasks. Furthermore, we need to compare with state-of-the-art tools like Magellan, like Famer. All of them should be compared with us. However, what we took out as a takeaway is information propagation has shown useful. It is a useful approach for general data integration tasks and should be used more often. This, however, brings us to 2 suggestions for promising directions. We should do automatic domain knowledge usage and also emphasize the usage of information propagation with graph-based methods. So this ends our talk. And we would like to thank you for your attention.
And we're open for questions.